Hello and welcome to lesson 2.3, Graphs of Rational Functions. Today we're going to review what a rational function is and how to draw it. So first of all, we're going to talk about reciprocal functions. If g of x is our function x squared minus 4, then the reciprocal to this is y equals 1 over x squared minus 4. Now some terms that we may remember that we talked about before. Something like a vertical asymptote. Well, vertical asymptotes occur whenever the denominator is equal to 0. So what you do is you take your denominator, set it equal to 0, and solve if you can. Again, many different ways to solve it. In this case, I get plus or minus -2. So a vertical asymptote is a spot where the function doesn't actually exist at that spot. So what I'm going to do is I'm going to draw vertical dotted lines right here. Now, also, we've talked about intercepts. So an intercept for this, you have a y-intercept when you let x equal 0. So in this case, the y-intercept is -1 over 4. Notice you cannot have an x-intercept. In other words, you can't have when y equals 0, because in order for that to occur, the numerator has to be equal to 0, or a possibility equal to 0. So there is no x-intercept. And we also talked about horizontal asymptotes. So horizontal asymptotes come from the end behavior of the function. And what you're doing is you're looking as x approaches infinity. You think of very big numbers that can be put in for x. So things like 1,000 or 10,000 or 100,000 or 1 million and so forth. You check out those values, and you'll see it approaches the value of y getting closer and closer to the value 0 just from above. So in other words, there are going to be positive values or values bigger than 0. And then you do, as x approaches negative infinity, you also get y approaching 0 from above. This gives us our horizontal asymptote as the equation y equals 0. So what I'm going to do is I'm going to draw a dashed line at y equals 0. Now, we could also draw y equals x squared here, minus 4, which was our original graph. Pretty good sketch of it. Or something close to it. And once you have that drawing, then you can come up with your reciprocal function. Your reciprocal function will go through all the points listed already above. So it goes through -1/4. So that's 1 point. Has no x-intercept, so that's not getting there, but it's getting close to these horizontal and vertical asymptotes, and it's got to be in the same domains as the original function g of x. So the original function g of x was defined to be positive for values less than -2. So our reciprocal will also remain positive and get close to these asymptotes. It'll also cross where this value is equal to 1. It'll also cross and be greater than 0 when x is greater than 2. So cross at y equals 1, right here, and get close to these horizontal and vertical asymptotes again. The last part, in between -2 and 2, that is where our original function g of x was negative, so our reciprocal will also be negative. It'll only cross at values of -1 when the original function was -1. And again, get close to these horizontal and vertical asymptotes. And this black function that we've drawn right now would be our reciprocal function. Okay, moving right along. Let's take a look at another graph. So this function right here, this function can be described as a quadratic over a quadratic and can be reduced and factored. So our numerator could factor into 2x plus 1 and x plus 3. Our denominator could factor into x plus 3 and x minus 2. Well, as you'll notice, the x plus 3's can be canceled from both the numerator and denominator, but once you cancel that, it simplifies our expression into 2x plus 1 over x minus 2, where x cannot equal -3, or x can't equal 2. Just like before, if your denominator ever equals 0, you'll get a vertical asymptote. Again, your horizontal asymptote is described by your end behavior. So as x gets larger towards infinity, choose big numbers, see that y gets closer and closer to 2 from above. Also, as x approaches negative infinity, y will also approach the value of 2, but in this case it will approach from below. So again, you just have to choose values into your calculator and see that that works out. Now, because we factored out the x plus 3's from the numerator and denominator, and x can't equal -3, this is going to be a spot in your function that doesn't actually exist and creates what is called a hole. So you will get a hole at x equal to -3. If you want to find out where the y value is of that, you just substitute it into f at x, and you get an approximate value of, let's see, if I substitute -3 in, I'll get -5 or -5, which will be at +1. So that's where our hole will actually occur. This one does have a y-intercept and an x-intercept. So if I substitute 0 into the original function, I'll get 1 over -2. So our y-intercept is -1/2, or 0 and -1/2. Our x-intercept, when can the numerator equal 0? Well, that's when, again, x could equal -1/2. Different point, that would be -1/2 and 0. Okay, so let's take a look at some of this stuff and draw these pieces. So we have a vertical asymptote at x equals 2. We have a horizontal asymptote also at y equals 2. Coincidence that these two things are at the same location. No worries. Also, it is a coincidence that the y-intercept and the x-intercept are both at -1/2. So again, we've got to get close to these asymptotes. And we've got to go through these points. We also have a hole at -3 and 1. So I'm going to draw that hole right there. So we've got to get close to these asymptotes, go through these points. And draw our function. Now, because there's no x-intercepts past the value of 2, so the only option that could get close to these horizontal asymptotes and vertical asymptotes must look something like this. And there's a pretty good sketch of f of x. You could try choosing some values like x equal to 3 or x equal to 5 just to see where those points might actually occur. Now, you can also notice some more end behavior here for this function. Not only as it approaches the horizontal asymptotes, but also as it approaches the vertical asymptotes. So as x approaches 2 from the right, this is what we say, with a plus sign almost as an exponent to the 2, you'll notice the y values get closer and closer to positive infinity. And as x approaches 2 from the left, y approaches negative infinity. So these are ways that we can describe the end behavior of the function and how we can work out what this graph would look like. Okay, so let's try one last one. Okay, so again, I'm going to factor my numerator and factor my denominator. My denominator is the only one that could be factored here, so x minus 6 and x plus 3. Numerator is x minus 3. Nothing that can cancel. Okay, so my vertical asymptotes would occur at x equal to 6 and x equal to negative 3. Now, if that didn't factor nicely, we could use quadratic formula to actually solve this. Again, you can investigate for your horizontal asymptotes as x approaches infinity. Choose very, very large values and see what happens to the values of y. In this case, y approaches 0 from above. As x approaches negative infinity, y approaches 0 from below. So again, choose very large numbers, substitute them in, and see what you get. You can also do the same thing for other end behaviors. So first of all, our horizontal asymptote is y equals 0. So I'm going to draw my horizontal asymptote, and I'm going to draw my vertical asymptotes. Okay, so again, some intercepts. Let's see. I have a x-intercept. So the numerator will equal 0 when x equals 3. So there's my x-intercept. My y-intercept. If I let x equals to 0, I get negative 3 over negative 18, which is 1/6. So my y-intercept turns out to be 0 and 1/6. So may I also suggest you choose values very close to 5. My apologies, very close to the values of 6 from the left and the right, and very close to negative 3 on the left and the right. So as x approaches, let's say 6 on the right, y approaches, substitute it in, you'll notice it approaches infinity. As x approaches 6 on the left, y approaches, substitute in, you get negative infinity. As x approaches negative 3 on the right, y approaches positive infinity. And as x approaches negative 3 on the left, y approaches negative infinity. So now that we have these pieces of information, we see our end behaviors I'm just going to draw the ends of the graphs here for each one. We only have two intercepts. We have an intercept of x equal to 3, or 3, 0, and a y-intercept of 0 and 1/6. So get close to those asymptotes, follow the function, and draw. This is the first instance where you see a function can cross a horizontal asymptote. It is possible for a function to cross a horizontal asymptote. It's just not possible for a function to cross a vertical asymptote, because that alters the definition of an actual function. So this is our function f of x. And there's a quick review of all the skills about graphing rational functions.